even Brazil, China, Paraguay, okay. So most of the South Asia countries still behind. Of course, we have to respect the people. If they don't accept the crop, then we just have to do the traditional way. But keep in mind that GM, genetic engineering, is not sort of a terrible term. I think that's just the technique. It's no different from traditional breeding. When you do a breeding, you introduce 1,000 genes, but nobody cares. But when you introduce one gene, people scared. This is called monster product. It's not. I think it's more important what you introduce into the crop. Okay, so that's a question we wanted to be more concerned in the future. Okay, so as I mentioned, the major transgenic crop today would be soybean, canola, that's a kind of an oil crop, and corn, cotton. And the trait, major trait alter would be insect, herbicide, virus, vitamin A, that's a golden rice, and then oil content or oil quality, because we wanted to have a not only high oil content, but also more unsaturated crop, okay? And then also delayed fruit ripening, and so you have a longer shelf life. And then I think that most of you already knew the two popular methods for plant transformation. One is using the agrobacterial, that's a natural sort of pathogen, very effective to deliver this plasmid, TI plasmid into the plant chromosome, okay? Even occasionally in the forest, you can see the tree. These are all agrobacterial caused tumor, okay? And another method is this particle gun. And in our lab, we developed another new method, no tissue culture whatsoever. Basically, we take the pollen and we introduce a foreign gene into a pollen, and then if you can do pollination by a breeder, then the seed you produce are transgenic. Okay, so that would save time, and almost high school can do that. So we have a patent with that, and some of the company, biggest agriculture company, working with us on that. And the very first transgenic crop commercialized is this what we call flavor saver. Basically, what they did is they use antisense to suppress the gene on the cell wall, on the skin, so that after fruit ripen, it would not become soft. Okay, so delay the cell wall softening, and so they can be harvested when they are fully mature or ripened in the field, and then still stay firm on the shelf of supermarket. And better yet, no pathogen would get in if the cell wall still intact. Okay, so this is the very first one, but it's not successful commercially because people say, okay, we can harvest later, or we can buy more ripened fruit from the supermarket. We don't need to have a genetic engineer a flavor saver. Okay, yeah. And of course, everybody know BT corn, BT soybean, BT whatever, BT rice. In the past, we grow this bacteria, and then they produce this BT toxin, which is toxic to the insect, but it's not to mammal or human being. In the past, they grow the bacteria and produce this BT and spread on the leaf. And now, scientists take this gene, introduce into a number of crops. So basically, this BT, when the insect eat, they would generate a big hole on their stomach's membrane, so become leaky, and then they die. Okay, so this is the best example, okay, of genetic engineering, and also very popular these days. Like cotton. In the case of cotton, probably more than 85% of the world cotton production is by BT cotton. Okay, and so you can see that this is a transgenic corn, non-transgenic, and this in some of the insect from the root or stem. Some people complain the BT crop, because they produce a flower containing or pollen containing the toxin, may be destroy the ecotype of this butterfly. Yeah, but we don't see really a conclusive evidence for that. And of course, the BT cotton is probably the most successful for the farmers, because they reduce the amount of insecticide, but also reduce the risk of toxic problem by the farmer, and then less pollution to the environment. Okay, and another example is in Hawaii. About 30 years ago, Hawaii's papaya industry went down the tube because of this virus problem as shown here. And then they use this coat protein on virus. This is a coat protein. So they engineer the coat protein in papaya. That would delay the virus infection. So very successfully saved the papaya industry in Hawaii. I heard a story in Taiwan. Even Taiwan government prohibit the cultivation of GM papaya, but some farmer already grow that. So we are guinea pig by self already. Yeah. But anyway, this is another big story. And then of course herbicide. All this herbicide tolerance engineering done by Monsanto. Of course, this is called Roundup Ready. That's a herbicide Monsanto tried to push. Okay, so this probably allow the big company to save to earn a lot of money. So that's why a lot of resentment from the consumer. Say, oh, you big company just do all the engineering and make a big money. So what happened to the farmer? What happened to the consumer? We don't benefit from that. So why do we want to risk our life by eating GM crop? So that has a lot of resentment. But for science itself, it was very successful. Yeah, you reduce the chemical, and then just a little bit over 10 years ago, this is more beneficial for the consumer. Okay, in many countries, vitamin A deficiency causes eye blindness, and then they don't have enough vitamin A. So the Germany, Peter Meyer and Potricus, they try to take 3 genes from plant, daffodil, and then maybe a bacterial, 2 bacterial genes, and insert into rice. This is the first generation golden rice, okay? And this is what they call maybe 3rd generation. You can see much more much more golden color, because a higher accumulation of vitamin A on the allelon layer. But don't forget, recently I make a trip to Thailand, and in Vietnam and Thailand they grow this crop called gek fruit. Usually it's like a shell, and this is a ½ kilo. When they ripen, it looks like a ½ kilo. And then you open up, it's all kind of lycopene, carotenoid, and then vitamin C extremely high. And if you take one fruit and put it into your rice, when you cook them, it all looks like this. So you don't need to do genetic engineering. So I just got the seed right now. I'm growing this crop on my balcony. So next time from Jiayi Dashi, come to my balcony. When I have this fruit, we'll have a party, and I'll cook this rice for you. Okay? Yeah. So you don't need to do genetic engineering. If you find something you can fortify your food, have higher nutrition. But I also want to mention that transgenic plant can be used as an edible vaccine. One of the good story is to cure the diarrhea, especially when the water is not very sanitary, yeah. And in Africa, my colleague, they take this vaccine and produce it in banana, and so you don't need a refrigerator to store all the vaccine. So all you need to do is just eat a few banana and you are cured. Okay, and then they can also produce the vaccine in the tuber, in potato, and you just eat like a salad. Okay, so this is convenient. Okay, and then so why we promote plant as a bioreactor to produce foreign protein? Okay, there are many systems you can produce foreign protein. Many of the medicine we use actually produced from bacterial, yeast, or fungi, or now people try to push insect or mammalian from the chicken, from the milk, or transgenic animal system. But I think the plant system is most safer because all these can be infected by virus except plant. Okay, and then plant has another advantage: low cost. You just save the seed, and whenever you need it, just grow it up. Okay, so I won't get too much detail into that. And then in plant, you can produce the foreign protein in the leaf, fruit, or seed, flower, tuber, root, or even suspension cell culture. So many different versatile tools can be used. Okay, in our department, one of the young faculty, Dr. Chen, some of our National Jai University students from Indonesia probably knew that. When Dr. Cohen discovered this what we call epidermal growth factor, human epidermal growth factor, that protein can heal your wounding. And then he received Nobel Prize in 1962 with this Dr. Mattaucini, yeah, right. And they received this, and they looking for some commercial potential. They say, okay, what about surgery? After surgery, you have to heal your skin, right? Regrow. So the first commercial application of this human epidermal growth factor is to be included in the cream after surgery, and then they heal better. Okay, but the market still limit. So how many people would have a surgery a year? Now they look in the biggest commercialization potential, put into the cosmetic, the cream. And how many ladies would like to have a new skin instead of like me, you know, old and suntan, everything. So now it's all in our high price skin protection, sort of a kind of a cosmetic product. Okay, so this is one good example. And Dr. Chen in our department tried to produce this from rice grain. So next time, ask him to give you some rice grain. You can make a powder and smear on your skin. Okay. Another example is this one. This is the silk produced by spider. It resists the fire and has the longest powerful. You can make just last week Japanese using 30,000 spider produced the silk and then make a violin strand. Okay, and they say the sound is beautiful, much better than the plastics. The strand. Okay, so this is being produced from corn in the U.S. So they want to produce this in large quantity and make a lot of product, commercial product. Yeah. Okay. Yeah, I'll try to finish quicker. And of course, I want to introduce some of my research. I have been trying to increase the yield in a number of crops, especially rice. So we have a project to increase rice by introducing the maize gene, C4 gene, into rice. And this project is supported by Bill Gates Foundation. Okay, so we want to boost photosynthesis in rice and productivity in rice by introducing the photosynthetic gene from maize to rice. So this is an ongoing project. Just quickly show you some of our transgenic 11 weeks, 14, 16, yeah. And they increase substantially in growth rate. And also, you can see this is a PP carboxylase gene from maize in rice. So when we have a high level expression, they do much better. Okay, same thing. And then we try to integrate the different gene from maize by hybridization. Okay. We also try to utilize the agricultural waste or biomass crop to make an ethanol. Okay, we can take the bacterial gene, express it in rice straw. When you harvest, they can be easily converted to ethanol. So we work with a biotech company right now. So that would be very beneficial to the farmer if we can recycle this. Okay, this is just an example how we can dissolve the cell wall from the agricultural waste and make it ethanol. This is the gene, first gene we introduced into rice at a high rate, and this is another crop we try to engineer. I think Indonesia just signed agreement with CPC in Taiwan to grow 4 million hectares in Sumatra. This is the jatropha crop. So our goal is to increase the yellow content, but also reduce the saturation. So that would be a much better quality. Okay. We also try to engineer the fragrance Phalaenopsis. Okay, so one gene can be used to produce roses smell. Okay, we demonstrate that already in sweet potato, but we need to wait a little bit. Okay, this one. So we basically take that gene called CPD gene, put it into Phalaenopsis, and they would convert some of the carotenoid into this roses smell. Okay, so we anticipate this probably in a couple of years. So we can do a tissue culture in orchid. We also use bacteria to find a number of useful genes, like a salt tolerance gene. So we try to introduce those genes into crop right now. So as you can see from my brief presentation, crop yield, stress tolerance, and then disease resistance, and then healthier food, and then pharmaceutical product can be engineered in the transgenic crop. And of course, the keywords biomedicine, edible vaccine, biofuel, phytoremediation, and then use the transformation system to study gene function. So that's our major area of research. So thank you. Yeah.
Wow, such a wonderful presentation, don't you think so, guys?